Alrighty, let's go ahead and get started. So last class, we started into the next topic, which is fluids. And what we found were a couple of big equations we're going to be using. The first was Bernoulli's equation. And this equation related or basically states that all of the processes which may give rise to the pressure acting in a fluid at some location is constant. That is to say, all of the factors which cause a certain amount of pressure to build into a fluid, maybe you have a pump which applies pressure trying to move the fluid through. The fluid itself is moving at a certain speed. The pipe system is at some height. All these different factors give rise to a certain amount of pressure in the fluid. And it turns out that for a pipe system, if you know the pressure at one location, that set of parameters which gives rise to this pressure is constant. So if I look somewhere else and I add up all those terms, I'll get the same number. And specifically, the equation says that the actual pressure in the fluid plus the term that deals with the velocity of the fluid plus the term that deals with the location or the height of the fluid. If you add all of those things together, you get a certain number. And that number is constant for the pipe system. So no matter where you look, you always get the same value. And so the way we show it as an equation is to say all the stuff for the first location is equal to the same stuff in the second location. Now, of course, this brings to mind fairly quickly conservation of energy. With that, you could check the total energy of a system at one location or at one time, and then check the total energy sometime later after something occurs, and you'll find that the total energy is the same. However, what makes up the total energy, kinetic and potential energies, those individual things can change and shift from one to another. So you drop a rock from head height. It's got a certain amount of gravitational potential energy, and it's not moving yet, so it's got no kinetic. But as it falls, the potential is being converted into kinetic. And so while the total energy doesn't change, each term changes such that when you add them together, you get the same number. Same thing here. You'll have a pipe system, fluid flowing through the pipe. And while the total pressure of the system remains constant, you can have at one location a smaller velocity and in a location a larger velocity. If you've changed the velocity, that means something else had to change to accommodate. In this case, the pressure. You increase the velocity, you lower the pressure, and vice versa. So that was the first big equation, Bernoulli's equation. This is the main thing we're going to use to calculate whatever it is we want to calculate. However, what we found was we need something else to help us, because a lot of times we will be given a problem that says, oh, the pipe constricts to some new size. And because of this constriction, how will the pressure change? Well, there's nothing in this equation that's staring at us that tells us anything about the size of the pipe. So how can we use this information? Well, it turns out that the velocity of the fluid which flows through a pipe is related to the size of the pipe. And the example I used is when you stick your thumb over the end of a hose, you constrict the opening of the hose, the water's trying to flow out. You put your thumb over part of it. Now all of a sudden the pipe is smaller because the hole is smaller. And in order for the volume flow rate, it's called basically the amount of water that flows through per second, to remain constant, what must happen is As you constrict the pipe, the velocity must increase. Okay, and it makes sense. If I tell you, you get 1 gallon of water per second out of this pipe, and then I constrict the pipe and I say you still need 1 gallon of water per second, but now the pipe is a lot smaller. Well, the only way to get the same amount of water flowing out of it per second is to make the water flow faster, so more water comes through. Since there's not enough room for the whole amount of water to come through, only a little bit of it can come through, then you must speed up the flow of the water so that you get the same amount coming out as is going in, for instance. And what we found was this equation, which relates that, is called the continuity equation. And a continuity equation simply is a relationship or a statement that the flow rate of a fluid is constant. And so the size of the pipe, and the way we measure the size in this case is by the area of the opening. So a lot of times it's called the cross-sectional area. If you have a pipe and you look at the opening, it's a circle. So the size of that circle is the area of that circle. And so that area times the speed of the fluid that flows through that part of the pipe. This thing is called the volume flow rate. It's an amount of water that flows per second. Must be equal to the size of a different part of the pipe times the velocity flowing through that part of the pipe. Right? If the volume flow rate is constant, then the flow rate at one position is equal to the flow rate at another position. And what is the flow rate? It's the size of the opening times how fast the fluid flows. And so what this would imply is that if you increase the size of the pipe, so now A2 is bigger than A1, well, V2, the speed of the fluid, must go down because A times V has to be constant. Whatever it is on the left is the same on the right. If I make A bigger, V has to be smaller. If I make A smaller, V has to be bigger. Thus, you constrict a pipe, the fluid flows faster. You expand the pipe, the fluid flows slower. And so this equation allows us to take information about how the pipe itself changes, the size, and convert it to a relationship of the velocity. How does the velocity change? And generally speaking, that's what's required to plug into Bernoulli's equation. And that's what we found out last time. Bernoulli's equation and a continuity equation, these are the two big equations we're going to be using to solve problems. Now, along with this, we also had a discussion about airplanes and flight and how airplanes are allowed to fly physically. And we found that one of the side effects of Bernoulli's equation is that if you have the speed of the fluid increase, then its pressure will go down. And if the speed decreases, the pressure goes up. And so what people did was they designed the wings on an airplane to be shaped in such a way as to force the air that flows over the top of the wing to move faster than the air that flows underneath the wing. Why do it that way? Well, if the air on top flows faster, that means the pressure or the force that pushes on it is less than the pressure or the force that pushes on the bottom. Well, if you have more force on the bottom pushing up than you do on the top pushing down, that just means you're lifting up the airplane. And so Bernoulli, one of the effects of Bernoulli's equation, or one of the things you could see from it if you investigate it, is that you can make things like flight, something that generally speaking should not float in the air. All of a sudden, you could force there to be this extra force lifting you up against gravity purely because of how the fluid flows around you. And by fluid, of course, we're talking about the air, gas. Of course, this is also true with water or any other fluid. Gases or liquids, it doesn't matter. So that's what we figured out last time. Now what I'd like to do today, of course, is to work some example problems. So let's try an example. For this example, you have a pipe. Oops, whose radius is, let's say, 10 centimeters, has water flowing through at a speed of, let's say, 40 meters per second. The pipe then expands to a radius of 20 centimeters. Calculate the change in pressure in the fluid. All right. So there's a nice example of a basic Bernoulli's equation type problem. How do I know? Well, when I read this question, I'm told about you have water or some fluid that flows through a pipe. The pipe is changing size, and you're being asked about pressure. Well, all that put together tells me this has something to do with Bernoulli's equation. Okay, fine. So what is Bernoulli's equation? Let me write it down. P1 plus 1/2 rho V1 squared plus rho GH1 is P2 plus 1/2 rho V2 squared plus rho GH2. This is the equation I'm going to be using. One thing I need to tell you is in the problem is that the density, let the density of water be 1,000 kilograms per meter cubed. Okay, that's just a constant about the material. The density of regular fresh water is 1,000. All right, so now I can start thinking about the problem. One thing you may want to do, if the problem itself doesn't do it, is draw a picture or visualize the system. What the heck's going on? So if I visualize this, I have a pipe of a certain radius with water flowing through it. So here's my pipe. I know that the radius here, size of this pipe, the radius, R1, is 10 centimeters. And then I'm told the pipe expands, so it gets bigger. So here we go, like this. So now that's the pipe. And I'm told this new radius, R2, is 20 centimeters. And water's flowing through, and I know the velocity of this water in this initial side, V1, is 40 meters per second. Okay, so there is kind of a visualization of this problem. The pipe is moving along, you got water flowing through it, and then the pipe expands to a new size. There we go. Now notice there's nothing in this problem that tells me anything about changing height. I'm not told I go up to the second floor or I'm going down a hill or anything like that. All I'm told about is the change in the size of the pipe. Well, that's good news. Because if that's true, if there's no change in height in my problem, then I don't have to worry about the term that has height in it. They cancel out. Now, why do they cancel out? Well, If there's no change in height, that means H1, the height of the first location, is the same as H2. And so rho GH1 is the same number as rho GH2. And so since they're on the separate sides of the equation, they cancel out. They'll just subtract off and you get 0. So I don't have to worry about them. Well, if I don't have to worry about them, then this equation becomes a little easier. Now all I have is P1 plus 1/2 rho V1 squared is P2 plus 1/2 rho V2 squared. That's nice. It's a little easier. And this is the equation I'm going to have to use to solve for what I want. Now, what is it I want? Well, I'm asked to calculate the change in pressure. But notice my equation doesn't say anything about the change in pressure. It has pressure at the first location. It's got something about the speed. And it's got pressure at the second location and something about the speed in that location. But I know, because I'm a scientist and we've been doing this before, when one says change in pressure, what one means is the difference in pressures. How does the pressure change? The final minus initial. So delta P, or change in pressure, really means P2 minus P1. Or you could call it P1 minus P2. It doesn't matter. It's the difference in pressure. How does the pressure change? Well, you were at one pressure. Now you're at another pressure. You subtract them. That tells you the change. So I want to solve for this thing, P2 minus P1. So take the equation and put P2 minus P1 on one side and everything else on the other. So if I do that, that means P2 is on the right side. So bring P1 over to the right. So now I have P2 minus P1. And then everything else is on the left now. So this 1/2 rho V2 squared, I have to move it to the left side. So it's 1/2 rho V1 squared minus 1/2 rho V2 squared. Okay. I just took my equation. I moved the terms around. I wanted to get P2 minus P1 by itself. So I moved the things over. And then everything else I just put on the other side. And in this case, it looks like this. So this is what I want. So I leave that alone. And now all I have to do is plug my numbers into this. Plug my numbers into that, plug it in my calculator, and I'll have an answer. That'll be the change in pressure. That's my goal. Now, before I do it, are there any questions about this? All right, hopefully it's making sense thus far. Now, in order for me to get an answer, that means I need to know what are all of these terms, right? Well, 1/2, that's a number, that's fine. Rho, do I know rho for my problem? Well, yeah, I'm given rho right there, 1,000. Do I know V1 for my problem? Yep, V1, I'm told, is 40 meters per second. Perfect. Do I know V2? No, I don't know V2. I know the first velocity. I know the density of my liquid, but I don't know how the velocity has changed. I don't know the velocity in the second part of the pipe, but I need it. Once I have that number, I can solve my problem. So I need to solve for the V2. That's now my goal. Well, how do I do that? I have a second equation. The second equation is the continuity equation. This equation is designed specifically so I could figure out what the new velocity will be. So what does it say? It says A1 V1 is A2 V2. All right, well, what are these things? Well, these are, if I think about my pipes as being these circular, pipes, cylindrical pipes, then each opening is circular. So the area of the first location is pi r squared for the first location times V1 is equal to pi r squared for the second location, it has V2. All right, so what is it I'm looking for? I want V2. That's what I want to calculate. So I bring everything else to the other side. So now I have V2 equals, well, there's pi R1 squared divided by pi R2 squared times V1. Right? All I did was divide pi R squared 2 over to the other side. And now I just plug my numbers in. First of all, the pi's cancel out because there's a pi on top and a pi on bottom. R1, the radius of the first location. Be careful. Remember, always in physics, we have to worry about what units we're using. Unless specified particularly, we will always use kilograms for mass, meters for distances and areas and volumes and stuff like that, and seconds for time. It's called the KMS units or the MKS units, meters, kilograms, seconds, always. So here I want the radius in the first location. I'm told the radius is 10 centimeters, but centimeters is bad. I want meters, so I have to convert centimeters to meters. But that's easy. 10 centimeters is the same as 0.1 meters. So 0.1 squared over the radius at the second location, 20 centimeters. Again, I have to convert that. That becomes 0.2 squared. All of that is multiplied by the original velocity, which is 40. And now I have my equation. So I plug everything in. 0.1 squared divided by 0.2 squared, get a number, times 40. And I get that V2 must be 10. So the velocity in the second part of the pipe is 10. Now, before I use it, can anybody tell me if this is right or wrong? Is this answer correct or is it incorrect?
Correct.
How do you know? You claim it's correct, but why? Why do you think it's correct? And what I mean is not particularly the exact number, but by looking at it, does anything look weird about it or does it seem okay? Anybody want to answer?
Because
Uh-huh.
V2 is less than V1 and R2 is greater than R1 because the pipe got bigger.
So why do you think V2 should be less than V1?
Because the pipe got bigger.
Very nice. Perfect. That's exactly right. In our intuition, remember, this is true in physics. Not so much in math, because math is generally speaking, we just have equations and we're getting numbers. In physics or engineering, depending on what we're doing, or chemistry or these other topics, we're not just solving equations to get a number. We have something physical we're talking about. And what makes us a scientist, rather than a pure calculator or a computer, is the fact that we can then use, once we get an answer, we interpret the answer. Does this make sense? How can we use this number? Things like that. And so we have to keep in mind when we do any problem in this class, what is it we're talking about? Don't lose track of the actual problem, the reality of the system. And so when I look at this, every time I do this type of problem, when I get this answer, I say, okay, does it make sense? I can't look at it and tell you if it's definitely correct, but I can look at it and tell you if it's definitely wrong. And the way I do it is I say, I know already conceptually that if I make the pipe go smaller, the speed should go up. And if I make the pipe go bigger, the speed should go down. So in this case, this particular problem, I have my pipe gets bigger. And so in the back of my mind, I know that in the second part of this pipe, the velocity should be less. So when I look at this answer, I better get a lower velocity than V1. And indeed I do. V1 was 40 and now it's only 10. So that makes sense. If I would have gotten an answer of 50 or 80 or something like that, then I could say, wait a second, I must have done something wrong. Maybe I plugged it in my calculator wrong. Maybe I forgot a square or something, because there's no way the velocity should have gotten bigger. Okay. Always, always, always take the extra 5 or 10 seconds to ask yourself, does this velocity make sense for the situation? And exactly as you said, because you know the pipe got bigger, this V2 should be a smaller number. And indeed it is. So perfect. Again, it might still be wrong. Maybe the answer should be 8. But I'm going to have faith that I plugged it in my calculator right. And at least looking at it, I don't see anything wrong. So I'll go ahead and use it. So now that I know this, I could go back to my original thing right here. That's what I'm trying to solve. So delta P, the change in pressure, is 1/2 rho V1 squared minus 1/2 rho V2 squared. Plug my numbers in. 1/2. The density, this is water flowing through the pipe, and I'm told the density of water is 1,000, so it's 1,000. Times V1, which is 40 squared, minus 1/2 times 1,000 times 10 squared. And there we go. We got all the numbers there. Now I could get my calculator out and plug everything in. And so let's see, what do I get? I get that delta P is 750,000 pascals. And usually these numbers are going to be kind of big. So if you like to use scientific notation, that's fine. Go ahead and use it. It's 7.5 times 10 to the 5th pascals. Okay. Now here's another thing you can do. This answer might become positive or might become negative. In this case, if you notice, what I'm checking out is P2 minus P1. So I'm saying, how much bigger or smaller is the second pressure than the first? What my answer says is the pressure in the second part of the pipe is 750,000 pascals more than the pressure at the beginning of the pipe. And I can again ask, does it make sense? Should it be more or should it be less? Well, just as I said before, if the speed goes down, the pressure has to go up. And if the speed went up, the pressure went down. Here, I'm told the speed went down because I expanded the pipe. And so since the speed went down, I expect the pressure in the second part to be bigger. And that's why I have a positive answer. If at the beginning of the problem, instead of solving for P2 minus P1, I did it the other way and I solved for P1 minus P2, well, then I'd have the same number. It'd just be a negative number. Because what it would say is the first pressure is 750,000 pascals less than the second pressure. Okay, so that's the difference between positive and negative answers here. We're talking about how does the pressure change? It can either go up or it could go down. In this case, the pressure went up because the pipe expanded and thus the velocity went down. And so I got a positive answer. So how do we do this problem? We have a problem. It's a pipe system, water flowing through the pipes, and we're talking about the pressure. This is Bernoulli. This particular example says nothing about the height. It's not changing up, or it's not going upwards or downwards or anything. It's just changing the size of the pipe. So that means I could cancel out the height terms. So that just leaves the other terms. I then say, what is it I'm calculating here? I'm calculating the change in pressure. And every time I do change in pressure, I do P2 minus P1. So I solve my Bernoulli for P2 minus P1 equals blah, 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 whatever's left. Then I say, do I have all the terms necessary to calculate it? And I don't. I don't know what V2 is. I know everything else, but I don't know V2. So before I can do my answer, I first have to calculate V2. So I switch over to the other equation, continuity. And I use a continuity equation. The area of the first part of the pipe times the velocity in that part of the pipe is equal to the area in the second part times his velocity. And I solve for V2. I make sure all my units are correct. I convert all my radius and all of that kind of stuff. And I get a final velocity. I then quickly ask myself if this final velocity makes sense. In this case, it does, because I expect the velocity to be less in the second part of the pipe since the pipe got bigger. And that's what I found. So perfect. There it is, 10. Now that I know V2, I now know everything I need to calculate the answer. So I just plug it into my equation and use my calculator and get a number. So are there any questions about this type of problem? What we're going to see, at least for this particular part of the topic, is all of the problems are going to be done with this method. Okay. Now, what can change is, what does the pipe system do? Does it expand? Does it constrict? Does it not change size? Does it go up in height? Does it go down in height? All that kind of stuff. I can come up with a load of different problems just by changing those things. However, whatever the system is, you start with Bernoulli, you keep whatever terms are important, solve Bernoulli for whatever it is you're trying to solve for. In this case, I wanted to change in pressure, but it could have been something else. Maybe I want to ask, what's the how high should the pipe system go? Then I want H2. Or what is the first pressure, given all of this other stuff that I'm solving for P1? Whatever it is, you have Bernoulli, solve for what you want, and then ask yourself, every term in this equation, do I know the numbers? If you already have all the numbers, then good, plug them in and get an answer. Sometimes, however, you don't know all the numbers. Like in this case, we didn't know V2. So we have to use something else, the continuity equation, to solve for V2. So you do whatever it is you have to get those numbers. And then once you have all the numbers you need, plug all the numbers into the Bernoulli equation you solve for and get your answer. All right. Now that's a basic one because it doesn't have all the terms. Let's try a more complicated version, one that has all the terms in it. So for this particular problem, I'm going to ask, find the change in pressure, just like before. But now I'll draw the picture. What we have is something that looks like this. Let's say here's my pipe system. Okay, what do I know about it? Well, R1, let's say, is 20 centimeters. R2 is 5 centimeters. I'm told, or the picture shows me, that my pipe travels upwards a distance of, let's say, 10 meters. And of course, I've got water flowing through. And I want to find out the change in pressure from the first location to the second. You may be a civil engineer designing someone's house, and you want the shower upstairs and the upstairs bathroom to get the right amount of water pressure so they have a nice shower. And so you say, what do I start with? The pipe's coming from the floor. I got to get it up to the second floor. And I'm going to design the pipe to constrict this much. Will that give me the amount of pressure I need? You know, maybe that's the situation. All right. So there's my problem. Again, just like before, this is a Bernoulli problem. I've got a pipe system with a fluid flowing through the pipe. I'm talking about the pressures. So P1 plus 1/2 rho V1 squared plus rho G H1 is P2 plus 1/2 rho V2 squared plus rho G H2. Now, one more thing I need to give you is assume the velocity in the first part of the pipe is, let's make it 10 meters per second. All right. So there's Bernoulli. Are there any terms I could cancel out? You let me know. Are there any terms like before I can cancel out from this particular equation? Anyone brave enough to guess? Yes or no? It's 50-50. No one's brave enough, huh? Well,
Would it be height?
Is there a change in height in my system?
Yeah.
Yeah. So if there's a change in height, then I need to keep the heights because that's going to be important. What about velocities? Will there be a change in the velocity in this problem?
Wait, so would it be gravity since there's not going to be a change in gravity?
Well, gravity, that's part of the term that has height in it. So even though the gravity doesn't change, because the height will change, you still need to keep, G. Basically, you've got three terms: the pressure, the term about velocity, and the term about height. If the height does not change, I could cancel out heights or the term with height. If the velocity doesn't change, I could cancel out velocity term. And the pressure, well, I'm asked to change in pressure, so I better keep pressure. So the question is, you already said there is a change in height for this problem, so I better keep the heights. Notice that's different than the last one. This last one, I didn't say anything about a change in height, so that's why I got to cancel it out. Now I do have a change in height, so I need to keep it, but what about the velocity? Do you think the velocity will change here? And how would you be able to tell?
Because the pipe size is changing.
That's exactly right. Since there's a change in the size of my pipe, there will be a change in the velocity. So unfortunately, I have to keep all the terms. There's nothing I can cancel out here. Okay, so since I have to keep everything, well, that's just the way it is. It'll look a little bit more messy than before, but it's no problem. We're all professionals. We can handle a little bit of algebra. Again, I want the change in pressure. So that means take this equation, have P2 minus P1 on one side and everything else move to the other. So I'm moving P1 to the right to join P2 over there. So I have P2 minus P1. And so I want to move everything else to the left. Well, what do I have? I have 1/2 rho V1 squared. And then I'm bringing the 2/1 over to the left. So that's minus 1/2 rho V2 squared. Then I have rho GH1. And then I bring rho GH2 over. So he becomes minus rho GH2. And there we go. That's what I want. Or that's what I have to use to calculate my change in pressure. I need all of those terms. Now, before I do it, I will show you, you may see it written in a more fancy way sometimes when people want to make you think they're masters of algebra. They'll actually write it like this. Notice this term and this term are the same, except one has V1 and one has V2. So they'll call it 1/2 times rho times V1 squared minus V2 squared. Okay, and then the rho GH terms, notice it's rho and G are the same for those two. So they'll say it's rho times G times H1 minus H2. Okay, Either way you like it. People that are fancy with their algebra, they'll do the green one. And the people that don't care will just do the blue one because that's what it is. You don't have to make it look more simplified. But just in case you see it somewhere else, how the heck do they get that? All they did was they factored and combined like terms. Okay, it's the same exact thing. All right, so do I know all of these numbers? Let's find out. Well, rho is 1,000. I already know that. This is 1,000. V1, I'm told V1 is 10, so I've got that. V2, I don't know V2. So I'm going to need V2. Rho G is 9.8. H1, do I know H1? Well, I don't really know H1, and I don't know what H2 is either. However, I do know that the difference, H1 and H2, the difference between them is 10. Right? I'm going from ground level, let's say, up to 10 meters high. So what we can do is just pretend that H1 is 0, and thus H2 would be 10. Okay. And I can do that because it doesn't matter. I can make H1 10, and then H2 would be 20. As long as H2 is 10 more than whatever value you stick for H1, it doesn't matter what you choose. It could be H1 is 100, H2 is 110. Everything will come out the same way in the math at the end of the day. So if it'll come out the same way, then why don't we make it as easy as possible? H1 we call 0, and H2 will be 10. That way the H1 term just goes to 0. It makes it, that's one less thing we have to worry about. So I'll call H1 0, that's ground level, and I'll call H2 10. So I know everything. The only thing I don't know is V2. So before we can handle this equation, we have to calculate V2. So we move on to continuity. A1 V1 is A2 V2. Solve for V2. V2 is A1 over A2 times V1. What is A1? It's pi r squared. So pi times R1 squared over pi times R2 squared times V1. Okay, notice the pi's canceled. They will always cancel, which is nice. So R1, what was R1? R1 is 20 centimeters, so that's 0.2 squared divided by R2. R2 is 5 centimeters, so that's 0.05 squared. All times V1, and what was V1? V1 is 10 meters per second, so times 10. So there we go. Get my calculator out, 0.2 squared over 0.05 squared times 10. I'm told V2 is 160 meters per second. Now again, before I use it, I'm going to ask myself if this makes sense. V2 is 160, V1 is 10, so the velocity went up. Should it have gone up? Well, let's look at the problem. I had a pipe that was big, and then it shrunk down to a smaller size. Every time you make the pipe smaller, the velocity should get bigger. So indeed, 160 makes sense. So I can trust this is the right answer. Now that I know V2 and I know all the other terms, let's go ahead and plug everything in. So delta P equals 1/2 times rho, which is 1,000, times V1 squared, V1 is 10 squared, minus 1/2 times rho times V2 squared, V2 is 160, plus rho 1,000 times 9.8 times H1. And remember, I'm going to call H1 0 because I have that freedom. I could call it whatever number I want, as long as whatever I call it, H2 is that number plus 10. So I'll call it 0. And then the last term minus 1,000 times 9.8 times H2, and H2 is 10. And now I have all my numbers. Okay. Before I calculate it out, are there any questions about where these numbers came from? All right, well, this term is 0, so that's good. Everything else I've got. 10 squared times 500 gives me, this is 50,000, minus 160 squared times 500 is 128,000,000 plus 0 minus 1,000 times 9.8 times 10, which is 98000. All right, add these together. So that plus 128,000,000 minus 50,000, and I get minus 128,48000. Or it looks nicer if you put it into scientific notation. 1.28 times 10 to the 1, 2, 3, 4, 5, 6, 7 pascals. It happens to be negative. And all that means, a negative answer is fine. All it means is that the pressure in the second location is this much less than the pressure at the beginning. But there you go. Here we have an example where everything's important. Not only are you changing the size of the pipe, you're also changing the height. So I use Bernoulli and I keep everything. I solve for delta P. Now that I have it, I need every term. So I need to know what every variable, the value of every variable, and I know everything except for V2. So V2 I solve using continuity equation and I get an answer. Once I have that, I just plug all the numbers into my Bernoulli equation and I solve for my answer. The only thing that's a little strange is the fact that I'm not actually told the actual heights. All I'm told is that the pipe goes from wherever it is to 10 meters above that. Well, the good news, just like what's true of conservation of energy, where your 0 point in height is doesn't matter. All that matters is the difference. And for instance, I right now I'm in my apartment. My apartment's on the 3rd floor. So if I'm doing an experiment, and let's say I'm doing conservation of energy, I'll hold my pen up into the air and I'm 6'5". So if I hold it up, let's say the pen is 6 feet above the ground. So I say, I've got a certain amount of potential energy, 6 feet worth, and I let go and the pen will fall down to the floor and gain a certain amount of kinetic energy. Fine. However, I'm on the 3rd floor. So the pen is not just 6 feet above the ground. It's 6 feet plus the height of my actual apartment. The fact that it's the 3rd floor. So shouldn't I make it 6 feet plus, another 30 feet? Well, the answer is no, you don't have to, because since the pen doesn't go all the way down to the ground level, it only hits the floor of my apartment, then I could just call the floor of my apartment the 0 height. Even though technically it's a certain distance above the true ground, I don't care about the true ground. All I care about is the difference between where it starts and where it ends. And same thing here. This pipe system might be at the, on the World Trade Center on the 100th floor going to the 101st floor. But I don't care about all the other floors. All I'm looking at is where did it start, where did it end? So you can always make the starting location 0 height. and the new location, whatever it is above 0. And that's what I did here. I'm told the difference in height is 10, so I'll call H1 0 and H2 10. And if you don't believe it's legal, if you think, oh no, I don't really understand that. What if it's some other number? Well, plug it in, do exactly the same calculation, but this time call H1 100 and H2 110. And I guarantee you'll get the exact same answer because the 100 will cancel out eventually. So since it doesn't matter what you choose the easiest. And the easiest is the lowest height is 0 and everything else is with respect to that height. That's why I call H1 0 and H2 10. All right, so any questions about this example? Now this example is as complicated as this is going to get. We had all the terms were all loaded into this problem. The pipe is changing size, it's changing heights, you're looking for the difference in pressure, everything's there. So if you can handle this and it all makes sense and you could get a blank sheet of paper and do it yourself, then any type of problem using Bernoulli should be fine. Obviously, I can ask for something other than delta P. I could have said, what should H2 be? What should the second height be if I want a delta P of 1.4 times 10 to the 7? Well, all that means is P2 minus P1 is now a number, and H2 is now the variable. So you solve for H2 instead. Same exact thing. Also, another thing to look out for, when these problems are given as word problems rather than pictures, you have to be able to interpret the words. Just like the first example, you have to be able to read that paragraph or that problem and draw the picture for it. And what you want to do is be careful, because sometimes you'll have things like this. You have a pipe whose radius is 10 centimeters, has water flowing through it at a speed of 40 meters per second. The water flows for 5 meters, at which point the pipe expands to a new radius of 20 centimeters. Then the water flows for another 20 meters from there. The question is, what's the pressure at this point? Well, the fact that the length of the pipe is 5 meters and 20 meters long, that doesn't matter. That's information that's completely irrelevant. I don't care how long the pipe is. I only care about 2 different things. What size is it, the actual circular radius of the pipe, and how does it change heights? But the fact that the actual length of the pipe is 150 meters long, well, who cares? That makes no difference here. So just be careful when you're reading some of these problems. A lot of times the problem, whoever makes the problems likes to put in some information to test whether you know what's important and what's not. All that's important is the size of the pipe, the speed of the water, and how the pipe changes heights. The length, how far the water goes, all of that stuff doesn't make any difference. So you can ignore that stuff. All right, so that's all I have for this. And with this, we're pretty much done this part of the topic of fluids. What we're going to do next class is get into Archimedes Principle. So number 1, we're going to talk about how does the pressure an object feel change as you go down deeper and deeper in the water. And that's true. That's why a lot of our oceans are not explored. Well, because once you go a little deep into the water, there's all that water is squeezing you, applying a lot of pressure, and our little frail human bodies can't take it. Even nice high-class submarines eventually get crushed if it goes too deep in the water. And so we'd like to figure out if we're going to be an engineer or maybe a mechanical engineer or something, and we want to design, or a naval engineer, I know UNO has a naval architecture as an engineering degree. If you want to design a submarine to go explore, maybe you want to find, the giant squid or things like, fancy marine life that no one's ever seen before. You have to be able to calculate whether your submarine can withstand these excess pressures. So we're going to find the equation that tells us how much pressure will you feel based on how deep you go. And then we're also going to do Archimedes Principle about buoyancy and how we can tell the density of an object based on how well it floats. Or if I tell you, for instance, you have an iceberg sitting on the water, and so you're looking at the iceberg, how much of the iceberg is below the water? And you could find out because there's a simple relationship between the density of an object and how much will be submerged in the fluid. And it turns out that about 10% of an iceberg is above the water, 90% is below the water. So when you look at an iceberg in a picture, you only see 10% of it. 90% is actually under the water that you don't see. And we can prove it mathematically. But also you can ask the question, I have a ship. How much of this ship will I expect to be submerged in the water? And all you need to know is the density of the ship. And it's a very easy relationship. So we're going to get on Archimedes stuff next time and finish up fluids. So if you have no questions, you're free to go and enjoy your weekend eventually. If you do have any questions, of course, let me know. Also, don't forget to check Canvas. I posted homework on this material. There's a homework problem. So, or I think it's two problems. So that's posted. It's due Tuesday. So you have plenty of time to work on it, but the sooner you work on it, the better. So don't forget to work on the homework problem, but also on Canvas. Of course, these recorded Zoom lectures are always posted along with these notes that I'm writing, but also the recorded lectures from last year are there as well. So if you want to supplement what we're doing, look at more examples and stuff, you could go check those out as well. All right, so that's it. That's all I have. You are free to go, and I will see you next time.
Have a good one.
All right,
Thank
you too.
you. Have a good
Thank you.
weekend.
You too. I appreciate it.